Hello everyone, in this video we're going to discuss something called Lewis dot structures, which you're going to see in a moment are really just an easier way of demonstrating the outer electrons for an element rather than having to draw every possible energy level that current element is possessing. Now with the electron configurations, for a quick recap, we were looking at following just the basic 2, 8, 8 rule, right? Where I can fit 2 total electrons in the first energy level, 8 in the second, 8 in the third, and actually just continues with 8 up into the 7th. But for us, we're never really going to go past the third. Maybe occasionally we'll have to go to the fourth and put a couple electrons in. So for Lewis dot structures, our focus is only going to be on the outer valence electrons, whether that's the first energy level, second, or the third. We're only going to look at the ones that are in the outermost ring. So let's proceed. Again, as I just mentioned, for Lewis dot structures, we're only going to take into account the outermost electrons, or valence electrons, because these are the ones that are going to be what we call reactive. They can interact with other elements around them. So if an element is using its third energy level, the third energy level are its valence electrons. Electrons in the first or second energy level are not going to interact with other elements. They're out of the picture. It's just the outermost ring. So to draw these, we're going to keep it fairly simple. We're going to continue with dots for electrons. All right, so the best you can when you draw on your screen, if you can, like I'm using my little stylus pen here. All right, you just draw the best that you can, a dot. Now, how are we going to proceed from there? Our electrons are going to be drawn one at a time, starting at the 3 o'clock position. You'll see what I mean by that in a second. And then we're going to move clockwise. Some teachers will teach counterclockwise. Some will say start at the top. Every teacher, every animation you go try to find, everyone does it differently. So we can all be consistent. This is the way I want you to do it on any other worksheets, quiz, or tests moving forward. So if I wanted to do carbon, now you already see it done down below, but how did I get there? So remember, carbon has the atomic number of 6, atomic number or mass of 12 rounded. So if I want to do the Lewis dot for this, I first have to write the symbol. And then I have to realize how many valence electrons that carbon has. If carbon has a total of 6 electrons, that means 2 are in the first, and the leftover 4 are in the second energy level. So that's my valence shell. So I have 4 electrons that I could take into account. So I'm going to start in the 3 o'clock position, which would be, again, normally right here. And now I'm just going to move clockwise until I do a total of 4 electrons. So 2, 3, and 4, just like the image that's below already. But again, the idea is you're starting right here in the 3 o'clock position every single time for an element. Now, all elements are going to want to reach what we call the octet rule, meaning that they want to reach that maximum number of 8 valence electrons in their valence shell to be considered stable. Every element on the periodic table pretty much is going to want to do this. The only exceptions are going to be hydrogen and helium, because each one of them only needs 2 electrons. All right, hydrogen and helium are in the first period of the periodic table. They only use the first ring. You can only fit a maximum of 2 electrons in the first ring, so they're the exception to the rule. So they're stable with 2 electrons, but everything else is going to want to use a total of 8 electrons in their outer valence shell, because they'll start to use at least the second energy level, third, or moving forward, etc. All right, so again, don't forget on our periodic table here, we're only now definitely going to be focusing on the valence electrons. Groups 8, 9, and 10, we said a bunch only have 8 valence electrons. When we hit group 11, we restart at 1 valence electron, 2 in group 12, all the way over to, again, group 18, where everything except for helium is going to want to have 8 valence electrons in its outermost shell. So let's do some examples now. So what I've done here already for you is I've already written how many valence electrons there are for each of these elements. So I don't have to keep going back and forth to the periodic table to show you. But half your battle will be just to find that element on the periodic table, see how many total electrons it has, and figure out how many of those will be in its outer energy level or valence shell. So for nitrogen, it has a total of 5 valence electrons. So again, I'm going to put the symbol N. I'm going to start in the 3 o'clock position and keep going clockwise. 2, 3, 4. And now at this point, if you have more, you start pairing them up. 5. So that's the correct Lewis dot structure for nitrogen. Now what this shows us very quickly is, now you don't have to do this, is that nitrogen needs what? 1, 2, 3 more electrons to become stable. So if it needs 3 more, it's going to want to get those electrons from some other element. So again, example, NH3. If I were to draw hydrogen real fast as a Lewis dot, it only has 1 electron. It only needs 1 more to become stable, so 3 hydrogens will bind to 1 nitrogen so they can all get the electrons that they need. That's going to be bonding later this week or into Monday. For oxygen, again, I write the symbol for oxygen. I have 6 valence electrons to worry about, so start at 3 o'clock. 1, 2, 3, 4, 5, and 6. There's your correct drawing. You can see that it needs 1, 2 more electrons to become stable. Again, you don't have to draw those lines. Fluorine is in group 17. It's one of the halogens we discussed. Everything in group 17 are the strongest elements on the periodic table because all of them, no matter which energy level they're using, they only need 1 more electron to become stable. So that makes them the toughest. So for fluorine, 1, 2, 3, 4, 5, 6, and 7. Again, it only needs 1 more to become stable. So maybe it gets that from fluorine, or hydrogen, I'm sorry. And HF would be hydrofluoric acid, a very dangerous acid. Silicon is right underneath carbon on the periodic table. All right, it has 4 valence electrons just like carbon. So again, 3 o'clock position, 1, 2, 3, and 4. Silicon is just as important and versatile as carbon. If we evolve using silicon as the backbone for macromolecules, we would be almost have some type of metallic properties, and we would glisten in the sunlight because we would refract light to a degree, because silicon can refract light. Now for argon, a noble gas, it's in group 18. We said everything in there is stable. It has 8 valence electrons, so 1, 2, 3, 4, 5, 6, 7, and 8. It is stable. It has reached its octet. It will never bind with anything else. And then finally for magnesium, it's in group 2. Magnesium has a total of 12 electrons, but it's only going to have 2 outer valence electrons. So we write the symbol for magnesium, start in the 3 o'clock position, and then we add the second electron, and boom, we're done that fast. So that shows me again that magnesium is missing now 6 electrons. It is very unstable. And what we're going to learn is eventually metals like magnesium, they're not going to get 6 electrons. So they'll just get rid of these electrons, drop down to the next energy level, which is filled, and now they're stable. But what they've become is what we call an ion, which has a charge because it's missing or it's gained too many electrons. And what magnesium will do is it can become attracted to anything else that also has a negative charge, because remember, opposites attract. They'll come together and form what we call magnesium chloride. All right, it would actually be something like this, would be the correct formula for it. But that's a salt. Just like sodium chloride, NaCl is a salt. So any crystalline structure or salt is actually as a result of electrons being lost or gained by an element. And that'll be what we call ionic bonding eventually. All right, thank you very much. Use this information for your homework this evening.